All right, welcome to the Chapter 4 Homework 1 review, the only assignment we'll have for Chapter 4. A lot of topics in here, some of them a little bit complex, but I would say we did pretty well overall. The average on this one was a 9.51 out of 12, so even a little bit better than we got in Chapter 3, and also, pretty good considering we had exam week preoccupying us for a lot of last week. All right, so let's go through some of the questions then. There are three major topics in this chapter. There's VSEPR, which allows us to determine molecular shapes. There's hybridization, which is part of that valence bond theory, the simpler of the bonding theories that we learned. Those two follow directly from Lewis structures. So really, as I'll show you, if you can do Lewis structures, and then you can predict both molecular shapes and hybridization pretty easily. The last topic was... All right, sorry about that. I had an unexpected visitor in my office. So as I was saying, the last major topic of Chapter 4 was molecular orbital theory, which is quite a bit different, a little bit more abstract of a way of thinking about bonding in molecules, but one that is nonetheless very important and very powerful for us. All right, so let's go and then start with these. So a lot of these are requests from students. So again, I appreciate the students that reach out to me and tell me the questions they have. Before I get into VSEPR, I do want to make sure we're clear on the difference between electron group arrangement versus the other way we classify molecules, which is molecular shape, geometry, or structure, as we sometimes call it. Hang on, my pen's not working. Gosh, what a disaster today. All right, probably a dead battery. All right, well, we'll eventually actually start doing this review. Here we go. All right, so we're talking about the difference between electron group arrangement and molecular shape or molecular geometry, or sometimes just referred to as molecular structure. A lot of different ways of saying the same thing. So remember that electron group arrangement is going to refer to all of the valence electrons around the central atom and so these electron groups are going to be either bonded atoms or lone pairs. So really it's the arrangement that all of these electrons take, and there are really only 5 possibilities for electron group arrangement, and it depends on the number of electron groups. So again, an electron group being an atom that's either bonded to the central atom, or it's going to be a lone pair, and there's only 5 possibilities that we talked about. So it's what we call the steric number, or the total number of electron groups, which range from 2 through 6. And so the electron group arrangement just depends on the number of these that you have. So you're going to have linear if it's 2, trigonal planar if you have 3 electron groups. I hope we're clear on this, but sometimes I don't exactly go through it as deliberately in class as I should, so I want to make sure we're clear. 5 electron groups is trigonal bipyramidal, and so again, these shapes are the ones that allow these electron groups to be as far away from each other as possible. That's really the basis of all of this. And so you have these 5 possibilities for electron group arrangement. Now within each of these, there's a lot of different possible combinations of bonded atoms and lone pairs. So then the geometry, or the shape, or let me spell it right, the geometry of the molecule, or the molecular shape, or sometimes just molecular structure, depends on the combination of bonded atoms, which we abbreviate as X in the AXE notation, and lone pairs, which we abbreviate as E. So there's a lot more possibilities for molecular geometry. So essentially they are subcategories of these electron group arrangements. Now, as we talked about, in a situation where there are no lone pairs on the central atom, the electron group arrangement and the geometry are the same. So these 5 electron group arrangements also are 5 of our molecular geometries in the situation where there's no lone pairs. But when you do have lone pairs on the central atom, you're going to have a different geometry, because essentially geometry is just the shape that the atoms themselves make up, ignoring any lone pairs in that descriptor. All right, so hopefully that's a little bit more clear. Just a quick review of that. Sorry for the frequent pauses. I had I'm having trouble scrolling on my tablet. It doesn't want to work on a Monday morning, but I need to. All right. Anyway, I'll stop being a train wreck eventually. All right, so going into the questions now, these are, again, mostly requests from students, a few that I identified from the results in Blackboard. So the first one is, according to the VSEPR model, the arrangement of electron pairs around NH3 and CH4 is asking, are they the same or different? And remember, this is talking about electron group arrangement, which really only is going to be determined by the total number of electron groups, not how many of them are bonds and lone pairs. So we have to draw Lewis structures for each of these. So NH3, sorry, we have 5 valence electrons from nitrogen, 3 times 1 for hydrogens. We have 8 valence electrons, and same for CH4. We have 4 valence electrons from carbon, now we have 4 hydrogens that each supply 1. So we have 8 valence electrons for each of these. Relatively simple Lewis structures. And then in NH3, we have to complete the octet of nitrogen with the lone pairs. So these bonds to hydrogen take up 6 of our valence electrons. We add 2 more to complete the octet and use up all 8 of the allowed valence electrons. CH4 is a perhaps simpler structure because there are no lone pairs. We just draw single bonds to each hydrogen. That's 8 valence electrons. That's complete octet on carbon. We're done. Now, if we look at the total number of electron groups on each of these, for NH3, the number of electron groups, we have 3 bonds to hydrogen, then we have 1 lone pair. So we have a total of 4 electron groups. All right. So again, it's 3 hydrogens that are bonded to the central atom, 1 non-bonding electron pair. That counts as 1 electron group. So that's a total of 4. For carbon, the number of electron groups, we just have 4 hydrogens bonded to the central atom, no lone pairs. So again, it's a total of 4. So both of these have the same number of electron groups, which means that the electron groups will be arranged in the same way. So the answer that would be correct is going to be D. The arrangement of electron groups is the same because in each case there are the same number of electron pairs around the central atom, 4 for both of these. So they're going to have tetrahedral electron group arrangements. They would have different molecular geometries because NH3 is a lone pair, which makes it trigonal pyramidal. Carbon CH4 does not, so that's going to just make this one tetrahedral. But the arrangement of electron pairs will be the same for both because they both have exactly 4. All right, so that was the first one that dealt with VSEPR. I'm going to skip this one because I have them in a weird order now. I think there's at least one more geometry question, right? I guess not. All right, so that's kind of a quick review of VSEPR. We're going to use that argument for a lot of these. Now, what we can learn then from VSEPR, one of the things that's able to come out of this is once we know the molecular geometry, we can predict whether it's polar or nonpolar. And there's a whole bunch of possibilities depending on the AXE notation, the number of bonding and non-bonding electron groups in there. So what's helpful to remember is that if you have, so remember we have this notation AXMEN, where M is the number of bonded atoms on the central atom, N is the number of lone pairs. If you have an AXM structure with no lone pairs, we could call it AXME0, those are going to be nonpolar. This is for situations where you have one central atom and one type of outer atom bonded to it, which is going to be true for most of these. If you have AXME1 with one lone pair on the central atom, no matter what, this is going to be polar. And then if you have more than one lone pair, there's a few possibilities, so I won't go through all of them. But essentially in this type of problem, we're looking for a molecule that has no dipole moment. No dipole moment is the same way as saying nonpolar. So we have to figure out which one of these is a nonpolar structure. So I'm not going to go through all the details of finding this, but for PF5, if we draw the Lewis structure, again, we can't skip that step. We have to draw a Lewis structure. We find that it's an AX5 structure, which means it's nonpolar. Again, any of the structures that don't have lone pairs in the central atom, one type of atom bonded to it, in this case fluorine, would be nonpolar. And the bonds are polar because there is still an electronegativity difference between phosphorus and fluorine. Remember on the periodic table we have phosphorus here, fluorine up here, so there's a significant difference in electronegativity between the two, but all of the bond dipoles cancel out whenever you have one of these AX AXM structures with no lone pairs. Now if we go to CHCl3, this one might be the one that's a little bit tricky. So CHCl3 does come out technically to AX4, but really it's better described as AX and then X prime 3. So it has two different types of outer atoms. And typically in this situation, if you have an AX4 structure but it's not four of the same thing, so this time we have one hydrogen and three chlorines, that's usually going to end up with, or I think always end up with, a polar structure. So if we look at CHCl3, it's tetrahedral, and normally if you have four electron groups arranged tetrahedrally, the dipoles would cancel out if they're all the same, but in this case they're not. So we have three chlorines. These are going to have dipoles pointing towards chlorine. But then the CH bond is pretty much nonpolar, but slightly polarized towards carbon, actually. So you have a small dipole going in this way. So all these dipoles don't cancel out, and this ends up being polar. So if we called it just AX4, we might be tempted to think it's polar, but it's really two different types of X's, and that makes it polar. Sorry, AX4 would lead us to believe it's nonpolar, but the fact that there's two types of X's makes it polar. So that one has a dipole moment. For PF3, we get AX3E, and anytime there's only one lone pair, it's going to be polar. D for N2O, what do we end up with? That would be, I believe N2O is going to be AX2. Let me check that real quick. Yeah, so N2O is AX2, but we have nitrogen at the center in this case. So maybe it wasn't so obvious here. We probably should have helped you out and told you, but in N2O, nitrogen is the central atom. Remember, the less electronegative atom typically is, which is nitrogen versus oxygen. So in N2O, you get this structure here, which has some formal charges unavoidably. Sorry, there's one of those is nitrogen. And so even though it's a linear molecule, you again have dipoles that don't cancel out. So you have one NN bond, which you would largely think of as being nonpolar, and then you have a dipole pointing towards oxygen that way. So this is again a situation where it is AX2, but really again it's better described as AX prime, two different X's, and that leads to a situation where the dipole moments don't cancel out. So that's going to be polar. Sorry, all the ones that are crossing out are polar. And then for SO2, this one's more straightforward. We get AX2E, and this is going to then be polar. Anytime you have just one lone pair, you can automatically know that it's polar. So that was easy for a couple of these. But PF5 is the only one that has no lone pairs on the central atom, is going to be nonpolar. So even though some of these were a little bit tricky to deal with, specifically choices B and D, which were, they didn't have any lone pairs, but they were still polar than any lone pairs in the central atom, still we can very obviously pick A as one being nonpolar because it's AX5, all five of the outer atoms are the same, so all the dipoles cancel out whenever there's no lone pairs on the central atom. Alright, similar type of question here. Which of the following molecules now has a dipole moment? So if it has a dipole moment, that's the same way as saying that it is polar. And so we have four choices here. One of these we can eliminate very easily, which is choice D, O2. This one is going to be nonpolar because anytime we just have two of the same atom bonded to each other, that's going to give you a nonpolar bond and a nonpolar molecule if it's just diatomic. So that one's nonpolar, we can cross it out. But we do have to think about BH3, SiF4, and SF4. So for BH3, if we draw the Lewis structure, this one's pretty simple. We just get AX3, no lone pairs on the center atom, only one type of atom bonded to it, so it's going to be nonpolar. Same argument as before. So this is nonpolar, so we can get rid of it. For SiF4, sorry, SiF4, not 5. For SiF4, this comes out to AX4. And again, I'm skipping some steps here. We do have to draw these Lewis structures, and if you're still a little bit unclear on that, make sure you review some of the previous notes in homework reviews. But if you draw the Lewis structure of SiF4, we get AX4, which again is nonpolar. No lone pairs on the central atom. But then if we do SF4, we would end up with AX4E. Alright, so SF4 would have this sort of Lewis structure, leaving out the lone pairs on the central atom, or on the outer atom, sorry, but we do have one lone pair on the central atom. So you really need to know how many lone pairs are on the central atom for these. This is AX4E, which is going to make it polar. Anything that has one lone pair on the central atom will be polar, so that's going to be our answer choice, SF4. Alright, so it really comes down again to Lewis structures, knowing how many lone pairs are on their central atom for being able to predict polarity. And then one more similar type of question. These are all requests for students. I do want to go through all of them at least quickly. Which molecule has no dipole moment? So we have water, we have xenon tetrafluoride, COSO2 BRF3. So no dipole moment means nonpolar. The one that is easy for us to eliminate is choice C, because again, it's diatomic, only two atoms. If the two atoms are the same, it's nonpolar. If the two atoms are different, it's polar. So CO is going to be polar because we have one polar carbon-oxygen bond, so it must have a dipole moment. Now the rest of these not as easy. A we should be able to do very quickly. H2O is AX2E2, which is one of the polar geometries. So we have tetrahedral. It's a bent structure here, is what it comes out to. So we have again dipole moments that reinforce in this direction. We talked about water a little bit in class. So this one's definitely polar. We're looking for the nonpolar one. If we go to XEF4, this one's one of the ones that's not as obvious from a polarity standpoint. So xenon tetrafluoride comes out to AX4E2. We don't have a lot of structures that are like this, but this is one that is. AX4E2. And again, is this one polar or nonpolar? You could just memorize the table that I gave in the notes, or we can draw it out. So xenon tetrafluoride comes out to be square planar. If I draw it in the plane of the page, that's easier for us to see it. The lone pairs would then be coming out of the page and into the page. So there are two lone pairs. This is an octahedral electron group arrangement. One of the lone pairs comes out towards you, one of the lone pairs goes away from you, but what we really care about is the arrangement of the bonded atoms, the dipoles. And in this structure we have dipoles pointing towards each fluorine, because fluorine is more electronegative than xenon, but they all cancel each other out. So we have these two that are 180 degrees apart that cancel. We have another two vertically arranged that are 180 degrees apart that cancel, so there's going to be no dipole moment, or it's going to be nonpolar. Alright, so AX4E2, when all the x's are the same, is going to be one of our nonpolar geometries. So that's going to be our correct answer. The rest of these we can go through quickly. We said C was one we could eliminate right off the bat because it's two different atoms. But if we have SO2, we saw this one earlier, that's AX2E. Anything with one lone pair is polar. So those are all polar, polar, polar. And then BRF3, we draw the Lewis structure, it comes out to AX3E2. This is T-shaped geometry, and that's going to be polar. Alright, so again, the ones that have two lone pairs, there's a few possibilities. You have AX2E2 is polar, AX3E2 is polar, but AX4E2 is nonpolar. So again, different possibilities. When you have two lone pairs, we have to make sure we're clear on those. But AX3E2 is a polar geometry T-shape. They don't all cancel out, so that's going to be polar as well. So again, the only one that works then is choice B, which is nonpolar. Alright. Now the next major topic we have, which also comes from the Lewis structure, is going to be hybridization. So we have a few different ones to go through here that are all very similar. These are cations, so maybe the Lewis structure wasn't as straightforward and obvious, but so we'll go through it. So pH2 plus, we have 5 valence electrons from phosphorus, it's in group 5. We have 2 valence electrons from hydrogen, or 1 each times 2 hydrogens. Then we subtract 1 for the positive charge. So this is going to have 6 valence electrons around the central atom. So when we do pH2 plus, we can only draw single bonds to the hydrogen atoms. And then we have one more pair of electrons, 6 total, so that's going to go onto the central atom like that. Now this is probably not expected to be a very stable species because it only has 6 electrons around the central atom. It has an incomplete octet. That's not typically very good. But if you had this type of structure, all we really have to do for finding hybridization is just counting the number of electron groups. So again, just like we did before for talking about electron group arrangement, the number of electron groups, we have 2 hydrogens plus 1 lone pair, so a total of 3. And then once we know the number of electron groups, whatever combination of bonded atoms and lone pairs it is, that can give us hybridization. So the following orbitals are available for hybridization. We have an s valence orbital, 3 p valence orbitals, and then when we go to the third row of the periodic table, So phosphorus is here in the third row, so it could, in principle, also hybridize a couple of d orbitals if it needed to, although that's sort of controversial whether it actually happens. But the point is we need to have 3 electron groups, we need to hybridize 3 orbitals. So we take the first 3 of these, which is an S and 2p, that makes this sp2 hybridization. So choice A would be correct. DSP is not even one of the hybridizations that we have, so that one we can eliminate right off the bat, but it's going to be sp2 because there are 3 electron groups. Alright, same song, second verse. Let's talk about the hybridization of chlorine in ClF2+. So we're talking about, again, another cation here. And if we go through and count electrons in this case, these are all group 7 elements, so the number of electrons is going to be 7 for chlorine, 2 times 7 for fluorine, so each of those has 7 valence electrons. We subtract 1 for the positive charge, and that gives us 20 valence electrons. Okay, so we have 20 valence electrons in this cation. We draw the Lewis structure, again starting with single bonds. We complete the octets of the outer atoms first, so same approach that we've been following. At this point, we've used up 16 valence electrons, 2 octets, 1 on each fluorine. So then we go with our last 4 going on the central atom. So this is going to be, if we wanted to categorize it this way, AX2E2, the number of electron groups is going to be 2 fluorines bonded to the central atom plus 2 lone pairs, which is a total of 4. So this time we have 4 electron groups. We have the same orbitals available to hybridize. 1s orbital, 3p orbitals. We could hybridize up to 2d orbitals. There are 5d orbitals, of course, but only 2 of them really would ever get hybridized. And what we end up with is for 4 electron groups, taking the first 4 of these, which is s and 3p's, so that makes it sp3. Alright, so predicting hybridization of the central atom is as simple as drawing a relatively good Lewis structure. You don't even need to worry about double bonds and things like that. If those are present, this wouldn't have double bonds, but if it did, it doesn't matter. We just count electron groups, 4 electron groups, 2 atoms, 2 lone pairs, makes it sp3. Alright, and then the last question here sort of asks us to think a little bit in more detail about the bonding in hybridized atoms. So this was a fill-in-the-blank question, and it says atoms that are sp2 hybridized form blank pi bonds. We're looking for how many here, if that wasn't obvious. We're looking for how many pi bonds can be formed when you have an sp2 hybridized central atom. Now this question is not worded perfectly, I would say, for reasons I'll get into, but again, if we think about sp2 hybridization, remember that what we have in total is 1 s orbital and up to 3 p orbitals. So if we're doing sp2, we still have 1 p orbital that's unhybridized. And remember, these unhybridized p orbitals are involved in pi bonding, so if we have pi bonds, they must use unhybridized p orbitals. So if sp2 has 1 unhybridized p orbital, that means it can make no more than 1 pi bond. Now it doesn't have to make 1 pi bond. There are AX2 structures that don't have pi bonds, so that's where this question is maybe not worded as precisely as it could be, but it would make at most 1 pi bond, so the answer we were looking for here was 1. So again, if you have sp hybridization, so to sort of follow up on this same concept, with sp you have 2 unhybridized, can't spell that, unhybridized p orbitals. That means you have up to 2 pi bonds. sp2 has up to 1 pi bond. sp3 you have 0 unhybridized p orbitals. So you would expect in these situations to have 0 pi bonds. Things get a little bit more murky when you start talking about hypervalent atoms that have more than complete octet, expand the octet of the central atom, so it gets a little bit weird there. But generally speaking, if you're talking about 2p elements, especially carbon, nitrogen, oxygen, and so on, if you have sp3 hybridization, you have no pi bonds. sp2 you have up to 2. sp2 you have up to 1 pi bond. sp you'd have as many as 2. So when you have these different hybridizations, if you leave unhybridized p orbitals, you are able to form pi bonds, and that's what this question was dealing with. Alright, and then this last question here on this same topic sort of combines 2 topics that we've been talking about, which is hybridization and dipole moment. So we're looking for which has sp3d hybridization and no dipole moment. So again, we're looking for a nonpolar molecule, but it has to have sp3 hybridization, sp3d, sorry. So sp3d hybridization means we have one s, 3 p's, and 1 d. That's a total of 5 hybridized orbitals, which means we have 5 electron groups. So the first thing we're looking for is which of these molecules have 5 electron groups, and then from there, if it's going to have no dipole moment, it's going to be nonpolar, meaning it's going to be an AX5 structure. These all have just one type of outer atom, so it's PCl3, BF3, SF4, mostly fluorine or chlorine. So for all of these, we're going to look for an AX5 structure with no lone pairs. That would be one that has 5 electron groups, but is going to be nonpolar. So PCl3, if we did the Lewis structure, is AX3E. BF3 would be AX3. So that's not going to even have 5 electron groups. This would be sp3, this would be sp2 if we want to do hybridization. SF4 would be AX4E. This would have the correct hybridization, sp3d, but it's going to be polar. So correct hybridization, but it's polar, so we can cross it out. These two don't have the correct hybridization. BRF3 is AX3E2. This is also 5 electron groups, so it's the correct hybridization, sp3d, but it's going to be another one that's polar. So correct hybridization, but polar. But then if we go to PCl5, we've seen this one or similar ones before. This is AX5. So this is going to be sp3d with 5 electron groups, but nonpolar. Alright, so this one asks us to combine 2 topics and also work backwards. If we give you the hybridization, you can then use that to figure out the number of electron groups. So we use this to figure out that there is 5 electron groups. And then which geometries with 5 electron groups are going to be nonpolar. The only one is AX5. So, you know, we have, actually we have 4. So for 5 electron groups, you have AX5, which is nonpolar. So these would all be sp3d hybridization because they have 5 electron groups. AX4E is polar. AX3E2 is nonpolar. And then another one that's not particularly common, but we do see sometimes, is AX2E3. This is linear. Sorry, I messed that up. I'm talking too fast. AX3E2 is also polar, but AX2E3 is nonpolar. Alright? So with 5 electron groups, we have 4 different geometries, 4 different subclasses, and they all have sp3d hybridization. The hybridization just depends on the total number of electron groups. But some of them are polar, some are nonpolar. So the ones that would be nonpolar would be either AX5 or AX2E3. The only one that works then would be choice E, which is PCl5. Alright, the last few questions deal with molecular orbital theory. Alright, so this one I don't think I intended to go over, but I guess I will. Alright, so we have molecular orbital diagrams for O2 and NO. Which of the following is true? So for this we have to draw these diagrams. Now NO, we didn't specify which diagram to use. Normally we would tell you if it mattered, because remember there's 2 different diagrams. For O2 we have this ordering. We have sigma 2s, sigma star. So this molecular orbital theory is a lot like we did for electron configurations. We just need to know the ordering of the sub-levels, the energy levels, from lowest to highest. And then we just need to fill them up with the correct number of electrons. The only difference here is that we can't use the periodic table to tell us the order because these are molecules, not atoms. But we have to remember these orders. For oxygen, we go in this way. So we always have the sigma and sigma star 2s. Then we have sigma 2p, pi 2p, the more conventional ordering, at least the more intuitive ordering. And then we have pi star and sigma star. Alright, so this is the ordering for O2. We didn't specify what it would be for NO, but I think for this question it doesn't matter. So for NO, we don't know if it's going to be this order or if we're going to switch these two. I think it's the same order, but as I said, it doesn't matter, so we'll just draw out the same order. So same set of orbitals for NO and just different numbers of electrons to put in. So we just have to populate these with electrons. O2 has 12 valence electrons. Each oxygen has 6. NO is going to have 11. So when we put electrons into O2, we did this one in class, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then for NO we have 11, so we're just going to have almost the same thing, but just 1 fewer electron. 10, 11. So the first one, choice 1, both are paramagnetic. So paramagnetic means they have one or more unpaired electrons. Oxygen here, O2, has 2 unpaired electrons. NO has 1 unpaired electron. So these are both paramagnetic, so that one's true. The bond strength of O2 is greater than the bond strength of NO. If we look at the bond strength, we evaluate that from the bond order. So for O2, the bond order is 1/2 times, again, number of bonding electrons. We have 2 down here, 4, 6, 8. And then we subtract the anti-bonding electrons, which is going to be 2 from sigma star 2s, 2 from pi star 2p, so a total of 4. So this has a bond order of 2. If we do NO for this bond order, we still have 8 electrons in bonding orbitals, 2 from down here, 4, 6, 8, the ones that don't have stars next to them. But this time there's only 11 electrons, so that means there's only going to be 3 that are anti-bonding. 2 from the sigma star 2s, 1 from pi star 2p. So this has a 2.5 bond order. Since the bond order of NO is larger, we expect it to be stronger, and this one says it the opposite. The bond strength of O2 is greater, so this one is going to be false. NO has the greater bond order and greater bond strength. 3. NO is an example of a homonuclear diatomic molecule. This is just definition. Homonuclear means 2 of the same atom, or really same atom. NO has 2 different atoms, N and O, so this one's also false. So that one we didn't even have to know anything about MO theory. And then finally, the ionization energy of NO is smaller than the ionization energy of NO+. This one we didn't really talk about in class, but it's the same concept as atoms. So if you have NO and you remove an electron from it, remember, each time we remove additional electrons, we expect the ionization energy to be larger, so this one would also be true. Another way to think about this also is that NO, the ionization energy, would involve removing this highest electron. If we remove that electron and make NO+, we now remove an electron from pi 2p, which is lower in energy. It takes more energy to remove it from the nuclei. So that one was a little bit beyond what we covered in class, but again, it's the same concept as atoms. Every time you remove electrons, the ionization energy becomes more and more difficult to remove additional ones. All right. Next question on MO theory was bond order of C2+. So again, this is pretty straightforward application. We had trouble with this one for some reason, but we're doing C2+. Technically, the ordering for C2+ is different than what we did in the last slide. So in the first half of the P block, boron, carbon, and nitrogen, the pi 2p comes first, and then the sigma. It doesn't really matter for bond order if you get this right or not, as it turns out, because we're just switching 2 bonding orbitals, so we're not going to change our calculation of the bond order regardless. But technically speaking, in C2 we'd have pi, then sigma. C2 plus number of electrons is going to be 7. Each carbon has 4 valence electrons. We remove 1 for the positive charge, so we have 7 electrons. So we go 1, 2, 3, 4, 5, 6, 7. Alright, so that's C2 plus. And then the bond order for this is going to be 1/2 the number of out of the 7 electrons, how many of them are in bonding orbitals? We have 2, 4, 5. And this is a problem. Alright, hang on a second. Oh, this is right. Sorry, I'm running myself in circles here. Alright, then we have 5 bonding electrons, 1, 2, 3, 4, 5, and then the anti-bonding electrons, we just have these 2 that are in sigma star. So 1/2 times 5 minus 2 is 3/2, or 1 1/2. So it's a 1 1/2 bond order. Again, fractional bond order in between single and double. Choice D is the correct one. Sorry, I didn't see that correct answer choice there. I was getting flustered. But it's there, and it's going to be 1 1/2 using this formula for calculating bond order. Alright, last sort of molecular orbital theory question. We have lithium-2 and beryllium-2. I forgot the subscripts here, but those are Li2 and Be2. And we want to know some things about whether they're stable, diamagnetic, and so on. So we gave you the diagrams in this problem. All we really need to know for these is the electron configuration. So each lithium is going to be 1s2, 2s1. Each beryllium is going to be 1s2, 2s2. So this time we gave you the full MO diagrams. Normally, as I said, we don't need to really worry about core electrons, we just need the valence electrons. So if we wanted to here, we could just remove these core electrons from the 1s. So there are these, MOs from the 1s orbitals as well, but we don't really need them. We can just ignore core electrons if we want, and just need to focus on valence electrons. So Li2 is going to have 2 valence electrons, each was 2s1. Be2 is going to be 4 valence electrons, each one is 2s2. We can ignore the core electrons if we so please. So for the 2 electrons in Li2, they just go into the sigma 2s. For Be2, we have 4 electrons, so we go 2 there and then 2 there. So the first question is, are they stable? Stable just means they have a non-zero bond order. So the bond order for Li2, we have 1/2, we have 2 bonding electrons, we have 0 electrons in anti-bonding orbitals if we're just considering the valence electrons. So this has a bond order of 1, so it's going to be stable. But then if we do Be2, we see that the bond order is 1/2. We have 2 electrons in sigma 2s, valence electrons only for considering that. We have 2 electrons in sigma star, and so we have a bond order of 0. In other words, the sigma bond is canceled out by the sigma antibond. We get a 0 bond order, so that makes this unstable. Alright, so then if we're looking for the correct answer, then we can eliminate the ones that would claim that Be2 is stable. So both are stable, can't be true. Be2 is stable, can't be true, because it has a 0 bond order. Be2 is stable, can't be true. So we don't even have to think about magnetic properties. We can eliminate all the answer choices, and choice B is correct. Now, is lithium-2 diamagnetic? It is, because both of its electrons are paired, but then this one says Be2 is unstable. So choice B is the only one that works. We didn't even have to think about magnetic properties, but Li2 is diamagnetic because it has both its electrons paired. Alright, and then finally the last one that I want to go through is use the molecules below to answer the next 3 questions. There's only one question here. Which molecules have equivalent CC bonds? This is in some sense more of a definition question and more than anything. It's just wanting to know which one of these has equivalent bonds. And part of the issue here is that the notation of these is a little bit weird. So if we have this ring here, remember that this structure is actually going to be 6 carbons bonded together, and then we have hydrogen on each one for C6H6. So each of these intersections is a carbon, and then we fill up the octet of carbons by making sure it has enough bonds of hydrogen. So that's sort of a shorthand notation for drawing these. Now if we go do C6H6 as we saw in class, we saw that there was 2 resonance forms. We have the alternating single double bonds. We could put the double bonds there, or we could put them in the other alternating positions, like that. So there's, in each of these cases, we have a 1 1/2 bond order, and all of the carbon-carbon bonds are the same. So this one is going to have equivalent CC bonds. If we go to C6H8, though, we don't have this delocalized situation because we don't have equivalent resonance forms we can do. Another way to think about C6H8 is that we have sp2, 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 sp2 for those 4, but we have also 2 sp3 carbons. And so in this case, for C6H8, we have C double bond C and C single bonds. So we have double bonds and single bonds. This bond here, you're not going to delocalize the electrons or draw a resonance form that has a double bond there. And then similar for C6H10, these single bonds between 2 sp3 hybridized carbon atoms, you're not going to have any delocalization. Remember that to have delocalized electrons, to have this resonance situation as we do in C6H6, you need to have unhybridized p orbitals. So what you can remember is that only sp2 carbons will be involved in resonance. So if you have sp3 carbons, which as we do in both of these situations with these single bonds here, you're not going to have any resonance structures that involve double bonds there. The double bonds can only move between sp2 hybridized carbon atoms. In C6H6, they're all sp2. So this is a little bit beyond what we did in class and something that's not going to be a huge topic, but one thing we just want you to remember is that in C6H6, which we call benzene, you have delocalized pi bonds, you have equivalent carbon-carbon bonds that have a bond order of 1.5, and so the only one that works in this case is going to be choice 1, which is A. In the rest of these, you have these carbon-carbon single bonds that are sp3 hybridized and are not going to have any delocalized pi electrons on them because they don't have empty p orbitals. sp3 hybridized carbons, all the p orbitals are hybridized, so you can't delocalize pi electrons. All right, that takes us to the end. I have to take off now anyway, but I think that covers everything that I wanted to get through. So hopefully that clarifies some of those topics. Please come see me if you need additional clarification or other questions on your assignment that you were not clear of. All right, thank you, and I'll see you in class.